So we have proved this Janson's inequality, and one of the thing is that we in this Janson's inequality, what we used is this setup. There is this finite universal set, and we have these independent, random variable. Each of them belong to R or not, and those have to be independent. And they form kind of elements of the events, and each events are the, combination of those independent events. But if you go over the proof of Janson's inequality, we have here what we actually used in this proof are, there are several things that we have used. One of them is that these BI are increasing events, monotonically increasing events that we have used. So we might wonder that, okay, we have this events B1 to, BI. So we have BI, where I is some index that we have these events. But we don't know whether each BI consists of some, some combination of each, so AI is say some x1 to xk, then this BI is, x1, x2, each of them are in R, are the independent events, and it's the combination of, intersection of these independent events. So assume that we don't know that. We only know that they are monotonically increasing. So, what here mean by monotonically increasing is that in section 6, we define give me a moment. So how did we define monotonically increasing? Yes. So again, we have a universal set, and each element there belongs to R. But now, so R is some random set in here. R is some random set in omega. But we don't know whether each element belongs to R in an independent way or not. We don't know that. And BI is, just some event that if it holds for R, then it holds for superset of R. So that's all we know. Or more generally, we can consider some finite distributive lattice L, and there, these sets are randomly chosen with the log supermodular measure that we have learned in the section 6. And there, you can define, increasing event. If it holds with R, then, in this poset, the bigger one also, if we choose bigger one, then this event also holds. Anyway, in that setup, can we say similar thing? So now we again define I and J dependent when Pi and Pj are not independent. So there are only two, so this is pairwise independent or not. So, and again, let delta be the summation of all probability, joint probability of dependent events. Then if you follow the proof of the Janson's inequality, then it actually holds. There are several points we need to be slightly careful. One of them is where did we use the so let me see. So this increasing decreasing events are okay. Yeah, one point is this. One point that has to be careful is that in the above setup before, whatever happens is on this di, d0 are related to the elements which are outside of AI. So AI and then our elements outside, whether they belong to R or not, was irrelevant of these elements in AI to belong to R. But now we have to actually ask whether these two are equal. Because what we know is each of BI is pairwise independent of this BJ. But pairwise independence is different from mutual independence. So there are several events, they are pairwise independent, pairwise independent, pairwise independent. But we don't know whether these all together we are pairwise independent or not. We don't know that. So we have to actually check that probability of BI is same with probability of BI assuming this D0. Because as we mentioned before, pairwise independence and mutual independence are different. Let's say this is one event and the other event. And this purple event is independent of blue event because this blue event happens with probability half, and conditioning this, this purple event happen with probability half. Conditioning on blue event, it happens with half, probability half. So blue and purple are independent. Purple and red are independent because assuming red event, purple still happens with half. But assuming this was maybe not so good picture, let's say. Yeah. Maybe this was not good picture. Let's make it a bit. So purple, blue, purple, red. Now, assuming blue and red both holds, the probability that purple holds is 1, which is not half. So pairwise independence and mutual independence were different. So we have to actually check this is holds, this is okay. And for that, we can just check this proposition. Let A, B, C be increasing event. And if A is independent, of each of B and C, then A is independent of B intersection with C, the joint event of B and C. The proof is not difficult. You just consider this. So you have B, C, and A. So what you do is you take the probability of these and these, and that's same as adding this probability and this probability. So this is most probability of AB joint event and probability of AC joint event. And because our assumption that the A is independent of B and independent of C, we have this. So this is actually equality. On the other hand, because of the assumption that B, A, B, C are increasing events, both of these are increasing event. So you use the FKG inequality, then this is at least probability of A times probability of B, C joint, and probability of A, B join C is probability of A times probability of B join C. Then what do we know? This plus this is this. And give me a moment. Yeah, and this plus this is nothing but this, because we know probability of B plus probability of C is B, C, same as probability of B all C happen plus probability of B and C happen. So exactly this. So what do we know then? This one is as big as this one is as big as this, but once you sum up, then they are equality. That means both of this inequality must be equality. Otherwise, this is strictly bigger than this. One of them is strictly bigger than this, then we cannot get the equality here. So, what do we know? Then this is same as this, meaning that the A is independent of this joint event. So we are done. So we can conclude that this Janson's inequality actually can be proved and can be used in the setup of setup where we have increasing events over a finite distributive lattice. Where we can use the FKG inequality. And there, if we have events and many of them are independent, then we can apply this Janson's inequality. Now we use that to actually, compute the probability that a given random graph is triangle free. So again, you consider the setup. So every, each H, each pair Ij is either H or not, which is, so our R is same as H set of G, where G is chosen from this probability distribution. So there, you consider each bad event being the, these three edges are all there to form a triangle. Then there are n choose 3 bad events. Each of them happen with probability P3, which is the expectation. And what's M? The probability that each of them doesn't hold is 1 minus P3. So it is not triangle, and there are n choose 3 many of them. So which is roughly e to the minus mu. And two sets T and S, which are triple, they satisfy this relation. So they are dependent only when they share an edge, at least one edge, but you cannot share two edges. So when they share two vertices, they are dependent. So how many such pairs are there? You choose n choose 4, so you choose 4, 1, and you choose two vertices which belong to both of them. Then you find two triangles. So choose 2 is 4 choose 2, which is 6. So this many pairs ST which are dependent. And for those S and T, the probability that both bad events happen is P to the 5 because we want to, the probability that both of them happen is these 5 edges are all present. So delta is n to the 4 times P to the 5. And mu is n to the 3 P to the 3. So now we compare these two. Which one is bigger? N to the 4 P to the 5, n to the 3 P to the 3. Then you have to check whether n p squared is bigger than 1 or not. So if p is little of n to the minus half, then n p squared goes to 0. So then in that case delta becomes little of mu. So Janson's inequality is that this is triangle free with expectation, negative mu plus delta over 2. That was the Janson's inequality. So, and this is little of mu, so this is more or less, e to the 1 plus little of 1, minus 1 plus little of 1 times mu. But what if this is not true? If p is omega of negative half, then this delta is, say, bigger than mu. So choose some constant here so that the delta is bigger than mu. There are some gap between these two cases, but which is essentially some constant times n to the negative half, but we ignore that. Then if this is bigger than some constant times square root of, n to the minus half, then delta is bigger than mu, then we can use the extended Janson's inequality. Then probability that G and P is triangle free is most e to the negative mu square of 2 delta. What is that? Mu square is n to the 6 p to the 6. You divide that, and this is roughly some theta times n square p. So here, this is most e to the negative mu, so we know that this is best possible. So gap between them is, this constant. And can we actually say similar thing? So this is at least e to the negative theta times n square p. Then, this is best possible up to multiplicative constant on the exponent. This is at least, this is indeed true, because this probability G and P triangle free is at least the probability that G and P is empty set, empty graph, having no edges. That's trivial lower bound. What's the probability that there are no edges? There are choose two pairs, and all of them are not chosen as an edge, which is 1 minus p. So this is roughly e to the theta times n square p. So up to multiplicative constant on the exponent, this is best possible. So this more or less determine the, probability that GMP is triangle free for pretty much all P. So next time we will, use this to prove that, so instead of triangle free, we can consider other graph free as well. So we will prove, but in general, for general H and for general P, proving it is a bit technical. So we will prove for specific H and specific P, we will estimate the probability of GMP contains no copy of H. So that's what we will do next time. And also we will consider a bit more on this variation of Janson's inequality. So Janson's inequality basically estimate the probability of x being 0, where x is the number of bad events happening. But can we still get some, other bounds, say that say this is too lower than expectation. So if we can somehow bound this in terms of t, then that's actually more general result than this. This is same as probability that x is smaller than mu minus mu. So we get something. So can we also get something along this line? So we will also think about that, and then we will consider some applications as well. That's what we'll do next time. Okay. Thank you for listening.